we were here. So we just got done developing the equations F equal MA along the normal coordinate. I mentioned it is, as far as the significance of this equation or application, this is actually an important one. That is the case if you have straight streamlines. So the radius of curvature is 0, then, and if it's horizontal, so and horizontal, you have a pressure variation only due to the hydrostatic pressure variation. And if it's, for example, gas flowing in a channel or a pipe, then, you know, unless the change in elevation is significant, we usually neglect changes in hydrostatic pressure variation. So this really has some implications on pressure measurement as well. For example, as I'll explain later, say you have flow in a pipe, and let's say it is a gas, and then you could put a U-tube manometer here, for example, and measure the pressure difference. You know, assume that the pressure, there is no variation of pressure across the pipe. So you're actually measuring the pressure at a particular location or the pressure difference between, well, it could be like, for example, if you drill a hole here and then put a U-tube manometer, okay, and this is open to the atmosphere, and then you could measure the local gauge pressure. And if it's assuming straight streamlines, assume that the pressure, you've measured the gauge pressure all along across the channel at this location. The other thing I wanted to, example I want to give, because it's still maybe a little hard to envision what is the significance of the normal direction. So suppose you have a flow with circular streamlines, and this sort of flow might be used as a model, say, for a tornado. So like a vortex, where you have the circular motion, okay? And then let's say this thing is in the horizontal. So we apply this equation here, and if it's in the horizontal, then this term would go away, and then we would have a minus partial p partial n equal rho v squared over r. So the normal direction, n, okay, this equation would then say that the change in the pressure in the normal direction is equal to this. Or if we put the negative sign over on the other side, the pressure decreases as you go towards the center of the flow. And at the center, there would be a pressure minimum. And that's kind of how vortices work. Okay? So this equation could be used to describe that basic behavior. Okay, but for now, we're going to apply the F equal MA along the streamline direction. Okay? So let me grab this equation. Copy. Oops. Paste. Okay. And recall that, so this is, so F equal MA along a streamline. So we're going to consider the flow along a streamline, and also recall we are assuming a steady flow, and it's inviscid, essentially frictionless, viscosity 0, okay? Now, so along the streamline, so let's multiply through, back to multiply by ds. So if we do that, okay, so for example, this term here, so dz ds is going to become dz, which is the change in elevation along the streamline direction. Okay? This term here, so first let's consider the fact that in general, pressure and the change in pressure in our flow can be determined by the change in pressure with respect to S, ds, plus change in pressure along the normal, dn. Okay? But since we are just considering a flow along the streamline, okay, then there will be no change in the n direction. Okay? So then we have just this, or that partial P partial S is equal to dP ds. And then our term dP ds ds is equal to then dP, which is equal to the change in pressure along S. And then this term here, dV ds ds, is going to be equal to dV. Remember, this velocity, there is only a velocity in the direction of S. So the speed, v, only changes in the along the streamline. Okay? So this is really dV ds, since we are assuming v doesn't change in time. And so this is a dV ds, and we have also that this is the change in v along S. So from here then, we can write minus dP minus rho g dz is equal to rho v dV. Okay? And it relates changes in pressure, changes in elevation, and changes in the velocity along a streamline. And this last term here, we can write as rho 1/2 dV squared. Because when you take the derivative, this would be 2v, and then 2v v, and then we would end up getting this. Okay? So then, okay, let me just make sure I'm doing what I'm supposed to be doing, following the notes. I think this podium is not big enough for me to. Okay, so then we have our equation which describes the changes in these quantities, and we can take the integral. Now, of course, let's see. Let me just, let's put everything on one side so that it is, everything is positive. Rho g dz plus rho, this is 1/2 dv squared, is equal to 0. And then if we integrate, okay, so we integrate, then we would get p plus rho gz plus rho v squared, this is just rho v squared over 2. If we can just pull this 1/2 in there, or here. So 1/2 v squared, and then the constant of integration. And that's it. Let me make sure that I got this right. I always, the way that I remember it is dividing by rho, we get p over rho plus gz plus v squared over 2 is constant along a streamline. So if we choose some streamline, and maybe at some point, maybe upstream, we know the values of all p, z, and v. Then we could evaluate the constant. And then the sum of these three terms is the same everywhere along that streamline. Okay? So you could apply it, this equation, between any 2 points along the streamline. So if we identify point 1 and point 2, then this equation would tell you P2 over rho. Let me just wait a second here. I went too fast. Let's go back up here. Integrate, integrate, and we integrate. What I skipped over was to very clearly indicate, assume rho, and for that matter, g, constant. Okay? Then we get this term, right? So then applying it between any 2 points, so this rho is a constant, so P1 over rho plus GZ1 plus V1 squared over 2 is equal to P2 over rho plus GZ2 plus V2 squared over 2. Okay? So, for example, if you know the pressures at these 2 locations and the elevation difference, and then maybe the velocity, then you can get from this equation the velocity at the other point, or whatever unknown for the particular problem. And this equation is referred to as Bernoulli equation. It's just a very simple algebraic equation, but it's very restricted. So the restrictions, so it's steady, we assume steady flow, we assumed inviscid, so frictionless, so it's an idealized flow because all real flows have viscosity. And we assumed density constant or incompressible, and it must be along a streamline. So just to emphasize, so Bernoulli equation, just to summarize and emphasize, Bernoulli equation, P over rho plus GZ plus V squared over 2 is equal to a constant. And then the assumptions, steady, inviscid or frictionless. Inviscid, sometimes we just refer to it as a frictionless flow. Incompressible, and along a streamline. So, very restricted, okay, but easy to use. And so it's often abused. Let me just note that the assumptions for steady and incompressible could be relaxed to get a more general form of the Bernoulli equation. So steady, so where that assumption came in is here evaluating the acceleration. Okay, we could consider an unsteady Bernoulli equation if we just left this term in there. Okay, and the other thing, we could consider density varying, so a compressible form, at this point when we integrate this term, then, or if we first considered going back to this term, or this where is it? Yeah, if we considered this, so let me write or dp over rho, so divide through by rho, plus g dz plus dv squared over 2. So this is 0. So if we integrate, then there is this term here. So the other two terms are just g delta z and, g, z, and v squared over 2. But this term, if we left it to allow for considering density varying, And if we knew how density varied as a function of pressure, it would be possible to consider that case and relax that assumption. Okay? But for the purpose of our class, we're going to always use this simple form of the Bernoulli equation and assume steady and incompressible, along with frictionless along a streamline. Okay? All right. So now, before I do examples, let me then just go over. So this came from Newton's second law, which is essentially conservation of momentum. Okay? And in general, we sort of have these two unknowns here, pressure and velocity, given the elevation or location of the streamline. And so for some problems, one needs to, in general, bring in another equation, two equations, two unknown, or in general, consider conservation of mass. So as I mentioned, the textbook, it's a little awkward because conservation of mass, although if we've, as I said before, if we've already had the thermo, MAE 11, then we know conservation of mass already. But the way the textbook does things and introduces the Bernoulli equation, conservation momentum first, there is not yet the formal development of the general conservation of mass equation. Okay? So I'm just going to go over a simple form that can be used when we solve these Bernoulli equations, because I'll go over some examples. Some problems, one needs to apply conservation of mass. For example, flow through a nozzle when there's an area change. Okay, so let's just maybe consider that case. So suppose we want to consider a flow such as this, okay? And we know that okay, so to be consistent, so if we assume steady flow in particular and inviscid and incompressible along a streamline, okay? But for the purpose of conservation of mass, if we consider the implication of these three assumptions. So first of all, this inviscid. So if you have flow through a nozzle like this, you have walls, okay? And if it's viscous, so if viscous, remember, you have the no-slip boundary condition. So, for example, at this location here, the fluid adjacent to the walls would stick to the walls, and if the nozzle was stationary, then the velocity would be 0. And then we would have maybe the maximum velocity at the center line, and we would have this velocity profile maybe similar to the one that was in your homework 1. The max velocity at the center, and then decreasing towards the wall and 0 at the wall. Okay? So, and then, you know, maybe this thing continues, and here, you know, we have still something like that. That's if it's viscous. But inviscid, if inviscid, so here we have the no slip boundary condition. If inviscid, then there is no slip, which means we have slip. So the flow, the fluid at the walls would slip, so they would have some velocity. They would slide, you know, this is frictionless. They would slide right past the wall. And so you may eventually just have this uniform velocity in this particular case, maybe a simple channel or pipe flow. Okay? All right, so there's that simple, the implication of that fact. So here we may have something, whoa, still not used to. So the velocity profile here may, we just have some uniform velocity here, and then maybe look something like that, our velocity profiles. Okay. Now, if you recall from MAE 11, the basic conservation of mass, so recall, it's going to look something like the time rate of change of the mass within our control volume. So the control volume, the so-called control volume where we apply conservation of mass, could be our entire nozzle, where we have an inlet and an outlet. So flow is coming into the nozzle, flow is going out. And in general, conservation of mass would say that how the mass changes within our nozzle depends on the total rate of mass flowing in minus the total rate of mass flowing out. Okay? And so this is, if you haven't had MAE 11, this is what you're going to learn. And so the implication of steady, basically this is an accumulation term. Okay? So if there is any mass accumulation, then the mass within this, whatever it is we choose as our system that we're applying conservation of mass to, is going to accumulate, change in mass, either increase or decrease. But we're assuming steady. Okay? So the implication is that the total rate of mass flowing in is equal to the total rate of mass flowing out. So mass coming in equal mass going out. Okay? So here there's only one inflow and one outflow. So we just have, for our steady flow, m dot in is equal to m dot out. And so if we choose the inlet, say the inlet is location 1 and the exit or outlet is location 2, okay, then the mass flow rate, that's mass per time, at location 1 is equal to the mass per time at location 2. Okay? M dot is mass flow rate, has units of mass per time. So in SI units, it would be like kilograms per second. Okay, and then if it's incompressible, okay, then the density is a constant. And one can, in general, express the mass flow rate when you have a constant velocity over the flow area. And then, you could identify the density at this location and then the flow area at this location, A1. So if it's a circular nozzle, it would be that circular area. Then the mass flow rate can be evaluated as the product of the density, area, flow area, and the velocity or speed. M dot being scalar. Okay? And then so we can also write rho 2A2 V2. So in general, the mass flow rate for our problems, and note that because we assumed inviscid, the velocity is uniform across the area, so that we can simply write this mass flow rate in terms of that uniform velocity, and then the density being constant. Okay? But if the density is constant, then we could cancel those out, and we get A1V1 equal A2V2. Velocity has units of length per time. Area has units of length squared. So this is length cubed per time, or a volume per time. And we can denote the volumetric flow rate with a capital Q. Okay? So not only is the mass flow rate constant through this channel, but the volume flow rate is also a constant, volume flow rate. So this is the extent of conservation of mass in our chapter 3. Okay? We're going to generalize it in further chapters. For example, consider a non-uniform velocity across the flow area, in which case the mass flow rate is expressed in terms of an integral over the flow area. But again, as I mentioned, chapter 3 requires just some simple knowledge, basic knowledge of conservation of mass to apply if needed. Okay? Especially in these problems where the flow area changes. Then you can see that V2, if you solve for V2, then that's A1 over A2 V1. Okay? So that for the steady incompressible flow, if the area, if the area decreases, okay, then the velocity has to, maybe I should just use this. If the area decreases, the velocity has to increase to conserve the volume flow rate. Okay? So for incompressible, we expect that a converging passageway would accelerate the flow. If the flow is going like this, we would have a diverging flow channel, and that would decelerate the flow. Okay? All right, very important to know. So I think that's all I want to do for the conservation of mass. Okay, typical units for SI, meter cubed per second, or English units would be GPM. What's GPM? Gallons per minute. Okay, so if you've ever measured GPM, you take a bucket, a gallon bucket, you got your hose, you got your watch. In 1 minute, how many gallons is coming out of that hose? And there you can get your GPM for your hose. All right. So let's, in fact, why don't we go ahead and now analyze this, problem. So maybe I could reproduce this. So as an example, a flow through a converging nozzle. So copy. Okay, so that was conservation mass. Now, just a few paste. Just a few examples of application of Bernoulli equation. So Bernoulli examples. Okay, so here's an example. What's this? Okay, so suppose we have flow through a nozzle, okay, and we don't really need, well, that's okay, yeah. Okay, and then we're going to assume, and maybe it's stated in the problem description, so we have steady, and steady and inviscid, or it could have been stated frictionless flow, and then we have incompressible, and so density is constant. Okay, so maybe it indicates explicitly in the problem statement, and we have flow through such a nozzle, and so now, well, let's just analyze it in general. Okay, so in the basic analysis, now, of course, depending on what you're asked to determine and what you know, you might approach things differently. But the standard procedure is, so once you've have a sketch of the flow and identify the known quantities, etc. Okay, then we of course also first, you might apply conservation of mass. And then you might apply conservation of momentum. So that's sort of the standard procedure if you don't know what else to do. Okay? Conservation of mass, conservation of momentum. That's sort of general. Now, some of these Bernoulli problems, as I'll show, may not need conservation of mass, and some do. Okay? So for this particular one, there's an area variation, and we expect then that we need to apply conservation of mass. And then we already did that, right? So we could write, rho 1, A1, V1 equal rho 2, A2, V2. It was incompressible. So we have this relation between the two velocities, V1 and V2. Now, the other equation, conservation of momentum, in chapter 3 is the Bernoulli equation. Okay? So that's the simplified form of F equal ma. And so if we have along a streamline, if we can identify a streamline, we can apply Bernoulli equation along that streamline. So for this particular problem, okay, the streamlines, so maybe I should have drawn it separate. So okay, so a flow like this. Well, the streamlines are, you're going to have the flow following the wall, right? Notice that the streamlines, and here's the centerline streamline. Notice that the streamlines are being squeezed together, okay? And as I'll explain later, that indicates flow acceleration, okay? Anyway, so we could choose the center streamline. So we choose a streamline, okay? And along that streamline, here's point 1, and then here's point 2, okay? So this is our streamline. Then, once we've identified the streamline and indicate the 2 points we're going to apply the Bernoulli equation to, then we can apply Bernoulli equation. So P1 over rho plus GZ1 plus V1 squared over 2 is equal to P2 over rho plus GZ2 plus V2 squared over 2. Okay? And then just in general, we're solving this in general, we could, for example, evaluate the pressure change. So P1 minus P2 is equal to, now for this particular case, if the nozzle is oriented horizontally, and you see that streamline is horizontal, so there's no change in elevation. So those two terms went away. And then V2, so the rho we multiply over on the other side, V2 squared minus V1 squared over 2. Oops. Okay. Now, let's say the areas are given. Okay, so we got the areas, or we could be given diameters. And so these are knowns. Okay, and you can see then essentially we have two equations, two unknowns, the velocities and the pressures, or the velocity change, the pressure change. Okay, and then maybe we are given, maybe we are given the information upstream. Okay, and then to determine the downstream. Then we could do this. Now, previously we had we expressed from conservation mass evaluated V2 in terms of V1. Okay, so you could substitute in. So we have rho A1 over A2 squared V1 squared minus V1 squared over 2, or rho over 2 V1 squared, and this is A1 over A2 squared minus 1. Right? Okay, so then P1 minus P2. So in theory then you could put a U-tube, so drill holes, small holes, we'll talk about this, pressure taps, and then connect our U-tube manometer like this, and then measure this height of our manometer column, and this would be related to the pressure difference, right? And then from this equation, if this is measured and we know the areas, we could use this equation to determine the velocity. And that is how some flow measurement devices work. You measure the pressure, and then it's calibrated, and you can get back the velocity. Okay? And there would be some, maybe some correction factor here that one would get when you calibrate this. Okay, so that's one example. Let's see, what other example? Okay, let me do the classic draining tank. So here's another example, the draining tank problem. Okay, so we may have some very large tank, a reservoir, that supplies water, maybe, and so we have some exit. Let me just simplify this. Okay, so there. And it's a very large tank and open to the atmosphere. So here's our free surface, and maybe there is water in here, and then it flows out here. Okay? And then it flows out to atmosphere. So the atmospheric pressure, surrounding pressure is P atmosphere. And as you'll learn, when you have an incompressible flow and you have a nozzle, okay, so you have fluid that is internal, and then it exits out into the atmosphere, okay? If it's incompressible, then the pressure right here at the exit is equal to the atmospheric pressure, okay? And so for all our problems that we're going to do in 101A, and most of the problems that in 101B, if you have flow exiting out to ambient or atmosphere, the pressure right there is atmospheric pressure. We'll learn when we study high-speed flows that may not be the case, and there's a mismatch. But anyway, that's for later, 101B. Okay, now let's say we have this height h, and this is a large tank. Oops. A very large tank, and it's draining. Okay, so assumptions. So in order to apply Bernoulli equation, we have to have a steady flow. But if we have a tank draining, well, this is one of those problems where the mass is going to decrease here, right? And so in principle, it is an unsteady flow. There's, going to be a dm dt in the tank. But we can kind of assume a quasi-steady flow. The tank is so large that essentially this draining is so slow that when we're analyzing it, it's essentially steady. And then the other implication of that assumption is that the surface, the free surface, the level of the tank, the water in the tank, is not going to change. And that the velocity of the free surface is 0 because it's such a large tank. Okay? We're also going to assume inviscid and incompressible. Water, incompressible, that's a good assumption. And inviscid, so we can get a very simple estimate of the flow rate out of this tank by assuming frictionless. Okay? And this just requires Bernoulli. as long as we then identify a streamline. Okay? So we want to determine basically the velocity at this location, and if we know the area of that exit, we can determine the volume flow rate. Okay? So what we want is the velocity there. The other place we have information is at the free surface of the water, because we just said that the velocity at this location, we're going to assume approximately 0. And then the pressure here is the atmospheric pressure. And actually, here at this location, P is also equal to atmospheric pressure, as I just mentioned. Okay? All right. So the streamline, then, we can envision a streamline, just a smooth flow that just goes from the top surface maybe to the center line of the exit. Okay? So there's our streamline. And now we can identify this point as point 1, this point as point 2, the 2 points along our streamline, and we can apply Bernoulli equation. So P1 over rho plus GZ1 plus V1 squared over 2 is equal to P2 over rho plus G rho 2 plus G Z2 plus V2 squared over 2. Okay, so the P1 over rho cancels because in both cases we have atmospheric pressure, and then V1 is essentially 0. And so then you can solve for V2 squared over 2, which is G Z1 minus Z2, or GH, the height, okay? And then V2 then would equal 2GH square root. So you can get a very simple estimate of the velocity and then the flow rate out of a draining tank. Okay? So that's an example. I had a classroom demo, and I'll do that Monday. And then we'll go further in discussing Chapter 3. And I think we'll be able to, I may actually show a video as well on Monday. We're going to discuss the different pressures: static pressure, stagnation pressure, total pressure, etc., dynamic pressure, and the measurement of. So very important. Okay, so homework 2 due Saturday, and look out for homework 3 on Chapter 3.